Chapter 3. Take a look at the end of chapter summary. There's a list of important terms right here, and we're going to go through the application of some of that material right now. We're at the stage where we're going to start talking about reactions, and in reactions we write the reactants on the left and then an arrow, and that arrow is going to turn out to be an equals sign, and then products on the right. Reactants on the left, products on the right. And the thing that we're going to take into account is something called stoichiometry. And stoichiometry is simply the numerical relationship between reactants and products. Do I have one reactant making two products? Do two reactants combine to make one product? That's stoichiometry. It's just the numerical relationship. And it falls under something that we call the law of conservation of mass, which means that matter cannot be created nor can it be destroyed. All of the matter that we're concerned about are atoms, and we're essentially going to do an atom count on our chemical equations. That arrow is an equal sign, chemical equation, where the total number of atoms on the left-hand side must equal the number of atoms on the right-hand side. So our law of conservation mass means number of atoms of reactant is equal to the number of atoms of product. I've written a couple of very straightforward chemical reactions on the board right here, and we're just going to go ahead and make sure that that law of conservation of mass is in effect. Carbon plus oxygen makes carbon dioxide. And here I have one carbon atom, and oxygen exists naturally as an oxygen molecule that is two atoms combined together. So C plus O2 makes CO2. I have one carbon and two oxygens on this side, one carbon and two oxygens on that side. I'll talk a little bit more about that in just a second. Here, if I wanted to make sodium chloride, again, chlorine exists naturally as chlorine gas, which is two chlorine atoms stuck together. So I need to make sodium chloride, and I've already learned that sodium is a +1 cation, chloride is a -1 anion, so that is a 1-to-1 ionic compound, sodium chloride. And because there are two atoms of chlorine here, that means I would need two atoms of sodium. So I put a big 2 in front of this number to tell me to multiply everything that comes after it. And remember, the subscripted 2 only multiplies the atom that immediately preceded the number. So two individual sodium atoms and a molecule of chlorine that contains two atoms combine to make two sodium chloride compounds. Okay, so the thing that's a little bit difficult here is that we cannot rely on nature just to provide us with atoms of everything that we want. Nature provides us with hydrogen and nitrogen and oxygen and chlorine and fluorine and bromine and iodine, all as diatomic molecules. And that's something that we're going to have to know and have to remember and to take into account when we write reactions down. And one of the types of reactions that we're going to see a lot of is a combustion, that is a combination with oxygen. And so every time we do a combustion calculation, we have to take into account that oxygen is provided to us by nature as O2. It would be easier for all of us if I could just say C plus 2O, two oxygen atoms, equals CO2. But there are no oxygen atoms on this planet. And so it's just disingenuous of us to write that down knowing full well that it's not how stuff comes to us. There are many different variations on how chemical reactions proceed. Let's look at a couple of the main types. The first one we're going to look at is called a combination. Combinations are also known as associations or additions or synthesis. Your book is calling them combinations. And in a combination, you take two, they don't have to be different, but two molecules or compounds or atoms, and you combine them by making a new chemical bond between those components. That could be something like a metal and a non-metal combining together, magnesium from group 2, two atoms in a molecule of chlorine from group 7 combining to make a salt, an ionic compound. So magnesium plus chlorine makes magnesium chloride. It could be two non-metals, sulfur plus oxygen, combining together to make sulfur dioxide. And we've already mentioned that combinations that involve oxygen are called combustions. The two components that are combining in an addition or an association don't have to be different from one another. It is possible to take nitrogen dioxides and take two of those and stick those together with a new bond between the nitrogens to make N2O4, dinitrogen tetroxide. Now, the exact opposite of a combination is a decomposition. And where combinations are sometimes called associations, decompositions are also called dissociations. And in a dissociation, you take the thing that has two parts bonded to one another, and you split that bond and make two completely separate entities. And it turns out that reaction that we just looked at, the nitrogen dioxide to dinitrogen tetroxide reaction, is completely reversible. And if we change the conditions, I can take N2O4 and separate it back into two completely separate molecules of NO2. Calcium carbonate, or limestone, when you heat it, decomposes into calcium oxide, lime, and carbon dioxide. That turns out to be a very important ancient piece of chemistry. Another type of reaction that we can look at are called replacements. Replacements are often known as displacements. And what happens in a replacement is that the reactant AB is already containing a chemical bond, but the other reactant C makes a better bond to A than B does. So AB plus C becomes AC plus B, and the bond between C and A is stronger than the bond was between B and A, and C has effectively replaced or displaced B from being in the original compound. If we look at a real-world example, in the halogens, group 7, if you're closer to the top of the group, you make stronger bonds. And chlorine is capable of displacing iodine from calcium iodide. So calcium iodide plus chlorine makes calcium chloride plus iodine. A development of that is the double displacement or double replacement, in which we have two compounds, and these compounds are going to switch what it is that they're holding onto. Now, if AB and CD are ionic compounds, we've already learned that A and C will be the metal cations, and that B and D will be the non-metallic anions. And so A is going to switch its counter-ion, its anion, B, for D, and C will have its D replaced by B. This is the basis of all of acid-base chemistry and is going to turn out to be fairly important. So this little molecule here, HCl, is hydrochloric acid, and NaOH is sodium hydroxide. This is an acid and that is a base. And we're going to switch the tail of this part of this compound with the tail of that one, and vice versa. And so AB plus CD makes AD plus CB, HCl plus NaOH makes HOH and NaCl. Acid plus base makes water plus salt. And acid plus base makes water plus salt is true of every single acid-base combination. Now, sodium chloride is table salt, and that's the salt that you may be aware of, but any ionic compound can also be a salt. The coefficients that we use in a chemical equation are not mass amounts. It would be very, very nice if we could just say iron plus sulfur makes iron sulfide, Fe plus S makes FeS, and because the stoichiometry here says 1 iron plus 1 sulfur makes 1 iron sulfide, that we could go to the stockroom, get a gram of this and 1 gram of that and combine them and make 2 grams of that. That's not how this works. And the reason why it doesn't work is when we look at the periodic table, an atom of iron has a different mass than an atom of sulfur. So taking a gram of iron and a gram of sulfur and combining them and expecting the same number of atoms in each of those two samples to exist is incorrect. That's false logic. If we took 55.93 grams of iron and we reacted it with 32.06 grams of sulfur, those two samples would contain the same number of atoms. So what we need to replace gram amounts in our calculations is a relative mass. And the relative mass that we use is something called the mole. So our coefficients that go into these reactions. Here, 1 iron and 1 sulfur makes 1 iron sulfide. Not gram amounts, mole amounts. And a mole is a relative mass. This little equation right here is very, very important. You must know this. The number of moles in a sample is the mass of that sample divided by the atomic mass of the element that you are looking at. And moles, they're not just for chemicals, they're for absolutely anything. You can have a mole of anything, but it does turn out that a mole is a stupendously big number. 1 mole of iron would constitute 55.93 grams. So 55.93 grams of iron would be 1 mole of iron, and it would contain 6.02 times 10 to the 23 atoms of iron. That is a huge, huge number. That number is called Avogadro's number. We use the mole to help us find quantities in chemical reactions. And one of the quantities that we want to find is called the theoretical yield. The theoretical yield is the amount produced when 100% of the reactants have reacted to completion. So I've set up a calculation that is set to find theoretical yield. And the question says, 3 grams of carbon burns in atmospheric oxygen to make carbon dioxide as the only product. How much carbon dioxide is produced in this reaction? the first thing that we have to do is write a balanced equation. None of your calculations are going to be meaningful unless you have a balanced equation. So C plus O2, remember O2 is delivered to us by nature this way, not as individual atoms. C plus O2 makes CO2. And then I'm going to convert my mass value in the question into moles. And what I have to also do is pay attention and find something called the limiting reagent. The limiting reagent is the reactant that is in the lowest mole quantity, not mass quantity, lowest mole quantity. And it tells us in the question that the oxygen that we use is from the atmosphere. And so we're going to assume that there is an unlimited supply of oxygen in this reaction, and that it's my 3 grams of carbon that are limiting the amount of carbon dioxide that I can produce. So here, carbon is the limiting reagent and oxygen is in excess. So moles is equal to mass divided by atomic mass. So the moles of carbon reactant is the 3 grams in the question, and look, I have 3 significant figures, divided by the atomic mass that I find off the periodic table. And that gives me an answer of 0.25. A quarter of a mole of carbon is available to react. Now what I'm going to do is find the stoichiometry in the question. And it says 1 carbon reacts with 1 oxygen to make 1 carbon dioxide. So for every 1 mole of carbon that I consume, I generate 1 mole of carbon dioxide. And because as a reactant I actually have 0.25 of a mole, the logic tells me that if I consume 0.25 moles of carbon, I will generate 0.25 moles of carbon dioxide. Now I'm going to use the formula mass of my product to convert the moles back into a gram amount. And all that formula mass is the sum of the individual atomic masses inside the chemical formula all added together. So my chemical formula says CO2, which tells me that carbon dioxide contains 1 carbon and 2 oxygen atoms. So I look on the periodic table and I find that carbon has an atomic mass of 12 and oxygen has an atomic mass of 16, and 12 plus 16 plus 16 equals 44. Using the same equation, moles is mass divided by formula mass. The moles of carbon dioxide is the mass of carbon dioxide divided by the formula mass of carbon dioxide. I'm going to rearrange that formula so that the mass of carbon dioxide is equal to the moles of carbon dioxide times its formula mass. So the mass of carbon dioxide that I get to use is 0.25 times 44. I'm going to generate 11 grams of carbon dioxide in this reaction. Let's consider the limiting reagent a little closer. It is the reactant that is in the smallest mole quantity, and it is going to determine just how much product can be made. So, as an analogy, if I had 8 hot dogs and 10 hot dog buns, the maximum amount of hot dogs that I could make and potentially sell if I were a vendor would be 8, because I need 1 sausage per bun. If I made this analogy be burgers, so that I don't have to have a top part of a bun and a bottom part of a bun, we'll have it be on Texas toast so that both pieces are the same. If I had 8 burger patties and 10 slices of Texas toast, then the maximum amount of burgers that I could make would be 5, because I need 2 of the slices of bread per product. So the limiting reagent in the top case is the sausage, and the bun is in excess, and there would be a remainder. And in the bottom case, the limiting reagent is the bread, and there would be burgers left over. Here's a question that requires us to use the concept of a limiting reagent and asks us something new. It asks us to find the percent yield. It says 10.00 grams of iron react with 10.00 grams of sulfur to make 10.00 grams of iron sulfide. What is the percentage yield for this reaction? Well, the percentage yield is the actual yield. So that's a quantity, a gram quantity, that will be given to you in a question, or you will measure experimentally in a lab. So that would be this number, the 10 grams of iron sulfide, because that's a product, divided by the theoretical yield. And the theoretical yield is that number that you calculate by using moles, that says if 100% of all the iron atoms available and 100% of all the sulfur atoms available were to react, what's the maximum mass that I could make? Actual divided by theoretical times 100 gives us the percentage yield. So we go about this the same way as we've done before. First, we need a balanced equation. The balanced equation is iron plus sulfur makes iron sulfide. These little lowercase s's in parentheses tell us iron is a solid, sulfur is a solid, iron sulfide is a solid. They're called state symbols. And our stoichiometry is revealed to us that 1 iron plus 1 sulfur combine to make 1 iron sulfide. So I have a 1-to-1 relationship between the reactants and a 1-to-1 relationship between the reactant and product. So what I'm going to do is find the number of moles of both of the reactants. And we find the number of moles. Again, moles is mass divided by atomic mass. For iron, the mass was 10.00 grams, and the atomic mass of iron is 55.93. If I divide those two, my answer is 0.1788 moles of iron are taking part in this reaction. If I do the mole calculation for sulfur, mass divided by atomic mass, I have 10.00 grams of sulfur from the question. The atomic mass is 32.06, and that gives me a number of moles of sulfur that is 0.3119. The smaller of these two numbers is the limiting reagent. That means that iron is the limiting reagent in this reaction, and that is the number that we need to consider moving forward. So now use stoichiometry to find the number of moles of product that could be possible. Well, the stoichiometry tells us that 1 iron makes 1 iron sulfide. 1 iron makes 1 iron sulfide. I know from my initial calculations that I don't have 1 mole of iron. I actually have 0.1788 moles of iron, which means that the maximum number of moles of iron sulfide that I can make is also 0.1788 moles. Okay, I'm going to use formula mass, because my product is a compound, not just an atom, to convert moles back to mass. Remember, moles is mass divided by atomic mass. That means that mass is moles times atomic mass, or in our case, formula mass, and all the formula mass for iron sulfide is the atomic mass of iron plus the atomic mass of sulfur. So the mass of iron sulfide is the moles of iron sulfide times the formula mass of iron sulfide. the moles we've determined was 0.1788. I'm going to multiply that by the sum of the atomic masses. I'm going to take the 55.93 for iron and 32.06 for sulfur and add them together and multiply them by the number of moles available. And that tells me that the most amount of mass that I can generate in this reaction for iron sulfide is 15.73 grams. The maximum mass that you can generate in a reaction, remember, is called the theoretical yield. And that leaves us to the very last part of the question, which is the point of the question itself. What is the percentage yield for the reaction? Well, percent yield is the actual yield, that's the number stated in the question, divided by the theoretical yield, that's a number that you calculate by figuring out moles, times that by 100%. So it tells us in the question that somebody has made 10.00 grams of iron sulfide. Now, we did say very, very early on that we cannot use mass directly in calculations, because if one were to assume that you have 10 grams of iron and 10 grams of sulfur, you might think that if everything reacted, you would make 20 grams of iron sulfide. That is an incorrect assumption. So if they then went on to tell you I made 10 grams of iron sulfide, you might think that the percentage yield is 50%, that you only made half as much as you were supposed to. That's not how this works. We have to take into account that iron and sulfur weigh different amounts. We convert them into moles. We find that one of them is in excess, one of them is limiting, and we work only with the limiting number. That gave us these numbers now. Actual was 10 grams. Theoretical was 15.73. If I divide those two numbers and multiply by 100, my answer comes out to be 63.57%. So taking 10 grams of iron and 10 grams of sulfur, combining them together to make 10 grams of iron sulfide is only 63% effective. Another application of the mole is finding the chemical formula for a substance from its percent composition. Here's a problem that we're going to work. Phosphoric acid contains 3.09% hydrogen, 31.61% phosphorus, and 65.31% oxygen. From this information, we can determine what the chemical formula for phosphoric acid is. The first thing that we're going to do is turn that percentage into a mole quantity. Now, moles are mass divided by formula mass, but there's no mention of mass in the question. But it does give us percentage. And so we do a clever little thing right here where we just assume that we have a sample, and that sample is 100 grams in size. Well, if I've got 100 grams of sample and hydrogen is 3% of my sample, that means that hydrogen makes up 3.09 grams of that sample. Okay? Moles is mass divided by atomic mass. For hydrogen, the moles of hydrogen is the mass of hydrogen from the percentage that we would find in a 100 gram sample divided by the atomic mass of hydrogen that we found off the periodic table. 3.09 divided by 1.008. That gives me a value of 3.06 moles of hydrogen in 100 grams. For phosphorus, the 31.6% in my sample is 100 grams. Therefore, in that 100 gram sample, I have 31.61 grams of phosphorus. Divide that by the 30.97 grams per mole atomic mass number that is on the periodic table, and the number of moles of phosphorus comes out to be 1.02. Do the same thing for oxygen. 65.31 divided by 15.99 gives me 4.08. So now I have three numbers. I have the mole values for each of the components in my chemical. What I'm going to do is take the smallest number. My three mole numbers were 3.06, 1.02, and 4.08. The number for phosphorus was the smallest. I'm going to take that number and I'm going to divide all of the numbers by this number, and that will give me the ratio. So 3.06 divided by 1.02 is 3. 1.02 divided by 1.02 is 1. 4.08 divided by 1.02 is 4. So hydrogen, phosphorus, and oxygen are present in the molecule in a 3:1:4 ratio. That means that the chemical formula for phosphoric acid is H3PO4. Technically, this is what we call the empirical formula. The empirical formula is the smallest set of numbers that you can use to describe a chemical formula. Sometimes chemical formulas, the real numbers are actually multiples of even numbers. And so there is an empirical formula might be different than the actual chemical formula. In those cases, what we would look to is there would be a second part in the question that told us what the formula mass for the entire molecule was. And we could fact check that the formula mass and the empirical formula mass both agree.